Hello, for this problem we have a spherical steel tank. So this tank has an outside diameter of 2 meters and a kind of wall thickness of 0.01 meters or 1 centimeter. So this kind of hollow spherical tank is going to be half filled with water with a density of 1,000 kilograms per meter cubed, kind of as shown below. We are asked to find the overall mass of the tank and the current location of the center of mass of this tank, this half-filled tank, measured from the base. So when we do this problem, I'm going to use the method of composite parts to kind of put together the center of mass. So first thing we need to do is define the axes. So we are measuring everything from the base of the tank. And so I'm going to do down here, if we do X, Y, it's kind of flat at the base, and then up through the center of the tank, we're going to have the Z-axis. Alright, the next thing I need to do is kind of break this down into the different composite parts that I'm going to put together. So I broke this down into 3 parts. I took a overall kind of spherical shell of this steel. So part 1 is a solid sphere. And it's going to have a radius. If our diameter is 2 meters, our outside radius is going to be 1 meter. Alright, part 2 is going to be a spherical cutout. And this, I just subtract off the thickness of the wall, so my inside radius for this cutout is 0.99 meters. And then part 3 is going to be my water. And so for the water, it's going to be a hemisphere or half a sphere. And it's going to have a radius, so hemisphere. And the radius is going to be the same as the inside radius of the tank, 0.99 meters. So these are my 3 different parts that I'm going to kind of put together for my method of composite parts. Alright, so I've got my 3 different shapes. So shape 1, 2, and 3. And since this is a kind of center of mass problem, I need to know the mass of each of these pieces. Kind of the intermediate steps, though, I'm going to need to figure out the volume based on just kind of the geometry of this whole scenario. And I've got the densities of the 2 different materials, the steel and the water. So I'm going to also make columns for volume and density. And that's going to lead to, if I multiply volume times density, I will get the mass of each of my components. Beyond that, I need to know the x, y, and z coordinates of the center of mass of each of these parts. So xi, yi, and zi. Alright, so let's go ahead and make our table. Alright, so starting out, let's find the volume of the 3 parts. And so the first one is a solid sphere, so before I take the cutout, I'm going to go ahead and figure out that volume. So the volume of a sphere, looking on my kind of centroid table, I can see that the volume of a sphere is 4/3 pi r cubed. So if I do 4/3 times pi times the radius of 1 meter cubed, I wind up with a volume of 4.189 meters cubed for my solid sphere. For the spherical cutout, it's going to be the same equation, 4/3 pi r cubed. My radius goes down to 0.99 meters though, and since this is a cutout, it's a negative volume. So negative 4.064 meters cubed for that. And the final one is the hemisphere. And so the volume of a hemisphere, looking that up again in my table, it's going to be 2/3 or half of the volume of a sphere. So 2/3 pi r cubed. and this is going to be a positive volume because I'm adding the water in. So R is again 0.99 meters, and my overall volume is 2.032 meters cubed. It's going to be half of that number up there. Alright, the densities are given to us. So the density of steel is 8050 kilograms per meter cubed. And then my cutout. So the cutout is actually no material, but imagine cutting this out of steel. And so I had the overall steel tank, and I cut away the steel in the center. So this is also, I'm going to count it as steel for part 2. And then for the water, the density of my water is just 1,000 kilograms per meter cubed. Alright, multiply these two numbers together. So volume times density will give me the mass, and for each of the 3 different shapes. So my overall mass is going to be 33,719.8 kilograms for that. I take most of that mass away with the cutout, so 32,718.3 kilograms. And then the water is going to be 2,032 kilograms. Alright, so now I've got the mass of each one of my parts. Next step is going to be to find the x, y, and z coordinates of the centroids for each of these shapes. So x and y, this thing is kind of symmetrical about the z-axis. And so if we can imagine the center of each of these shapes is going to be on the z-axis, which means that it has no x or y coordinates. So the x and y coordinate of the center of the overall sphere is 0 in the x, 0 in the y. Same with the spherical cutout, 0 in the x, 0 in the y. And for my hemisphere, it's also on the z-axis, 0 in the x, 0 in the y. Z is the only interesting direction in terms of finding the coordinates of this. Alright, so if we look at the center of the sphere, and so the centroid of a sphere is just the kind of innermost point, the center of that sphere. So if I've got a sphere that is 2 meters in diameter, if I go up 1 meter to the center, that is going to be the centroid of my sphere number 1. The cutout is centered on the same location, so that's also going to be 1 meter. And the kind of most difficult one is going to be my hemisphere. And so for the hemisphere, I would go ahead and look at a hemisphere in my centroid table for 3D shapes. And for the centroid of a hemisphere, I can see that going kind of from the flat side, which is going to be the top of my water surface, I need to go out by a measurement of 3/8 of the radius. And so 3/8 times the radius, this is going to be kind of going from 1 meter, I would go down by 3/8 of the radius. So 1 minus 3/8. And the radius of my hemisphere, again, is this 0.99 meters. And so that is where my z-coordinate of the centroid of that hemisphere is going to be. So if I do this calculation, I wind up with 0.629 meters. Alright, so now I have filled in my table. I just need to perform the calculations to find the mass, as well as the centroid coordinates. And so for the mass, I simply need to add up this column. So 33,719.8 minus 32,718.3 plus 2,032 kilograms. Add those all together. I wind up with a mass of 3,033.5 kilograms. And so I can use that in some of my later calculations as well. Alright, so that's my overall mass. I just added up the mass column. Next, I need to find x bar, y bar, and z bar. So x bar, I can kind of take a shortcut. So if the centroid of each of the components is at 0, the centroid of the overall object is going to be at 0. Same thing with the centroid or center of mass of the in the y direction. Since all of these numbers right here are 0, the overall centroid is also going to be equal to 0. Z bar, since I have 1, 1, and something that's not 1, I need to perform the calculation in this direction. So Z bar is going to be mass 1 times Z1 plus mass 2 times Z2 plus mass 3 times Z3. And I divide that whole thing by the overall mass. And so it'll be 33,719.8 times 1 minus, since this is a negative mass here for the cutout, 32,718.3 times 1 plus the mass of the water, which is 2,032 times Z for the water, the hemisphere, of 0.629. So that whole number gets divided by the total mass, and the total mass is what I just calculated up here, 3,033.5 kilograms. And so if I plug in all my numbers and solve for the final result, I'm going to wind up with Z bar of 0.751. And this is going to be units of meters. Alright, and so with that, I've taken my kind of spherical tank that's half filled with water, and I've figured out the overall mass and the x, y, and z coordinates of the center of mass of this object. So thank you for watching, and hope to see you again.